Hello and welcome to Chapter 9, Section 5, the sine and cosine ratios. The essential question is, how is a right triangle used to find the sine and cosine of an acute angle? What you will be learning is how to use the sine and cosine ratios, how to find the sine and cosine of angle measures in a special right triangle, how to solve real-life problems involving sine and cosine ratios, and how to use a trigonometric identity. Alright, so first thing we're going to do is we're going to talk about what sine and cosine are. So sine and cosine are ratios that are also trigonometric ratios for acute angles that involve the lengths of the leg and the hypotenuse of a right triangle. In the previous section, we learned about tangent, and tangent involved both of the legs of the right triangle, the opposite over the adjacent. Okay, now sine and cosine are also trig ratios, trigonometric ratios, but they contain two different parts of the triangle. So we're going to go ahead and start first with sine. Sine is represented by the opposite side of the angle over the hypotenuse. Okay, so for example, if we're trying to find the sine of A, okay, we would then take this opposite side here, opposite, over our hypotenuse, okay, and sine always goes over the hypotenuse, and the same things or similar thing goes for cosine. So let's say I was trying to find the cosine of that same angle A. To find the cosine, we would do the adjacent, which would be the angle that is connected to that angle or next to the angle, over the hypotenuse. Alright, so if we're trying to find the sine and cosine of the given triangle, let me go ahead and erase this part here first. Alright, so what we're going to be doing is we're going to be doing that same technique that we just did on the previous slide. So if we want to find the sine of angle S, we are going to first identify angle S. And from the previous slide, we know that to find the sine of any angle, we take the opposite and we put it over the hypotenuse. Okay, so what we're going to do here then is we're going to set that up for sine S. Sine S, we want the opposite side of sine of angle S, which is 63. And we're going to put that over our hypotenuse. Okay, so now our hypotenuse is 65. So we're going to put 63 over 65. I'm going to go ahead and type that in right here. 63 over 65. Okay, that would be the sine of angle S. Okay, which is 0.9692. Okay, rounded 4 decimal places. All right, now let's try again, but this time let's find the sine of angle R. Okay, so here's angle R. We're going to set the sine of angle R up as the opposite, 16, over our hypotenuse, which is 65. So then we would have 16 divided by 65, which is 0.2462, rounded to 4 decimal places. All right. Okay, so that's exactly what we're doing to find sine. All right, so now cosine is different. All right, so I'm going to go ahead and erase. So like the only thing that changes is our numerator. So for cosine, to find cosine, we're going to take, instead of the opposite side, we want the adjacent side. So the cosine of angle S. Okay, let's go ahead and start there. Cosine of angle S. Okay, for that, it would be adjacent, so 16, over our hypotenuse, 65. Okay, so if you notice here, sine R and cosine of S are exactly the same. Okay, and they're exactly the same because they follow these rules, right? For sine, it was the opposite of this angle, right? That would be that, over the hypotenuse. So since it's always over the hypotenuse, the sine and cosine would basically kind of be like the same for the two opposite acute angles. So the sine of S will be the same as the cosine of R, or the other way around. Okay, so then without even solving it, okay, cosine of R is going to be the opposite of the sine of the other angle, which is angle S. Okay, so we're expecting it to be 63 over 65. Now let's just go ahead and confirm that with the technique of adjacent over hypotenuse. So if we're doing angle R, we want the adjacent, which is 63, okay, so that's correct, over our hypotenuse, which is 65. So that matched up correctly there. So then our cosine of S is 16 over 65. And our cosine of R is 63 over 65, or 0.9692. All right. Sines and cosines, just like how we talked about, how it's like basically like if you have the sine of one angle, you would be able to find the cosine of the other angle. So that's because sine and cosines relate to complementary angles. And if we recall, complementary angles are angles that add up to 90 degrees. Right, so then if we let A and B, so if we have two angles, say A and B, we're going to just let those be complementary. So then A plus B is equal to 90 degrees. Okay, let's just keep that as our baseline for this slide right here. All right, so then the sine of an acute angle is equal to the cosine of its complement. Okay, so sine, let's say our angle is 35. So that means that its complement, in order to add up to 90, it has to be 55, right? So these two angles add up to 90, so they're complements. So then what I would say is that if I have sine of 35, okay, that's going to be the same number as the cosine of 55. Okay, so we're going to do an example on the next screen. The same thing goes for cosine. We can go back and forth. But we're just going to go ahead and go here as rewriting this trigonometric expression. So if we have the sine of 56, and it wants us to write this in terms of cosine. So sine 56 is going to be equal to the cosine of its complement. So what that means is we're going to go ahead and figure out what the complement of 56 is. And that how we do that is we just subtract 90 from it. So if we do 90 minus 56, okay, and then that's going to give you the cosine value that we're going to put in here. Okay, so that would be 34 degrees. So then we would input here the cosine of 34, because the cosine of 34 is the complement of 56, because they add up to 90. Then the sine of 56 is the same value as the cosine of 34. Okay, and then check this out. We want to make sure that we don't do this, okay, because this is not the correct value. We want to put this into degrees. So I'm going to go ahead and get a copy. Having some technical difficulties controlling this here. All right, point is, okay, we want to make this degrees. Okay, cosine of 34 degrees. Can't put the thing right now, but that's how you set that up. All right, so what if I wanted to find the length of the legs of a certain triangle? Okay, so here I have a triangle, and then I have a degree 26, and I have the hypotenuse, which is 14. So since I have the hypotenuse, it's going to be important that I know that I can't use tangent, because tangent is opposite over adjacent. So to find x and y, it would be very useless to do tangent 26 equals x over y because I have two variables and I can't solve it. So what we're going to do is because we have the hypotenuse, I know I'm going to have to use sine. Okay, so then here, if I do the sine of 26, okay, so 26 degrees here, the sine is equal to the opposite over the hypotenuse. So I'm going to do opposite x over hypotenuse 14. All right, and then that's going to give me one step to do to solve for x. So I'm going to multiply both sides by 14 or cross multiply. I could cross multiply, put this over 1, cross multiply, and it gives me x is equal to 14 times the sine of 26 degrees. Okay, so then we're going to go ahead and type that into our calculator. 14 times the sine of 26. And we should get 6.137. Okay, on this one we want to round up to the hundredth. So 6.14 is going to be our value of x. All right, and then we're going to find the value of y. So we're going to do the same thing with cosine in this case, because we want to find the side that is adjacent to y. Okay, adjacent to y. I mean to 26. So here's angle 26. Remember that the cosine is adjacent over the hypotenuse. So if I'm looking for the side that's next to the angle, then I'm going to use cosine of 26. That's going to be equal to y adjacent over 14, which is our hypotenuse. If I put this over 1 and I cross multiply, we're going to get y is equal to 14 times cosine of 26 degrees. Okay, and then all you have to do is come to the calculator, and go 14. This time we're doing cosine, still 26, and make sure that it's on degrees, not radians, otherwise you're going to get the wrong answer. So 12.58, and then there's a 3, so we're going to leave it as 12.58. I'd just like to point out something. If we know, I'm going to erase this part of the triangle here, but if we know that this angle here is 26, this angle here is 90, okay, then we know what the measure of this angle is, okay, because we know that all the angles in the triangle are going to be equal to 90. So if we do that, we can use, if we are only comfortable using sine maybe, then we could just stick to doing sine. So we know that this angle here is 64 degrees, because 64 plus 26 plus 90 is equal to 180. So if I wanted to do this one in a different way, I could have done opposite over hypotenuse, which is still y over 14. But in this case, I'm going to be doing, because I did opposite over hypotenuse, I have to use sine. But then this is going to be sine of 64. So then if I do cross that out, 14 times the sine of 64, that should still give me the same answer. I'm going to leave that one there so we can see it. So 14 times the sine of 64. Okay, and see how the answers are exactly the same. Okay, and that's how we know that this is valid. And we remember that sine and cosine work in basically opposite for complementary angles. All right, so here we're going to be using a special triangle. So because we have a 45-degree angle, we're going to go ahead and do the same method that we did on the previous lesson. So I'm going to create a right triangle that hopefully kind of resembles a 45-45 triangle. So let's say this is a right triangle. This is 45 degrees. This is 45 degrees. Okay, then we use what we know from special triangles, and we know that the side that is across from the 45 is equal to W. Across from 45 is equal to W. And then across the 90-degree angle, we have W times the square root of 2. Okay, and again, from the previous lesson, what we did is we made W equal 1, because that's going to make our calculations a lot easier. So then if we do this, 1, and then we change our W to a 1, so then that's just going to be the square root of 2. All right, so now I have this. So to find the sine of 45 and the cosine of 45, so sine of 45. And this is cool because for 45, 45, it's the same thing for both because they're both 45. So I'm going to use this bottom one here, and I'm going to do opposite 1 over hypotenuse, square root of 2. So then I would have 1 over the square root of 2, okay, which we're going to have to type into the calculator to get our value, 1 divided by square root of 2. And we're going to round 4 places, so 0.7071. Okay, that's what we're looking for. And if we're trying to find the cosine of 45, let's say this angle again, cosine is adjacent, which is 1, over square root of 2, okay, which is the same thing. So then these two values are going to have the same thing, 0.7071. Okay, now it's going to be different when we're trying to find the sine and cosine of 30 degrees, right? Because the sine and 30 degrees, they're different. So it's going to give us a different value, not the same. All right, let's say this is 60, this is 30, this is 90. So then that means the side across from 30 is our W. The side across from 60 is our W square root of 3. And the side across from the 90 degree or the hypotenuse is equal to 2W. Okay, so again, we're going to keep our calculations simple. We're going to change W's into 1s. And we have these as our values. So then here we're going to calculate this sine and cosine of 30 degrees. So what we're going to do here is to find the sine of 30. We're going to need 30. Sine of 30 is equal to the opposite 1 over the hypotenuse 2. All right, so that was pretty simple. We don't even have to use a calculator for that because we know that 1 over 2 is equal to 0.5, and then we need 4 decimal places, so I'm going to add 3 zeros. Okay, and then cosine 30, let's do that one in purple. Cosine 30 is equal to the adjacent side, square root of 3, over the hypotenuse, which is 2. So then we have the square root of 3 over 2, which we are going to have to come back here to the calculator. Square root of 3 divided by 2. So then we have 0.8660. There we go. All right. Here is our application to a real life problem. So let's say you're skiing down a mountain and the altitude that you're skiing down is 12,000 feet. So this is this side of the right triangle. Okay, the angle of depression. So here the angle of depression represents the downward line from the site that makes from the horizontal line that you're looking. So let's pretend if you're looking straight and you look down to the bottom of the mountain, that angle that it creates from straight to down, this angle 21 degrees is the angle of depression. Recall that in the previous lesson we did there was like a tree and you're standing here, and if you're looking to the top of the tree and you look straight, that creates an angle of elevation. Okay, but but this is the angle of depression. So this is how we know. Look across and then down. That's the angle of depression. All right, so let's find the distance x down the mountain to the nearest foot. All right, so first we got to see, okay, we have 21 degrees. Now we don't know if we're going to use sine or cosine, but we're going to see what we can do with this. We know that at the bottom, we have to have the hypotenuse. The hypotenuse here is x, so whatever we use, either sine or cosine, is going to have to be over x. Okay, so now let's look at what values are given to us. I know I have this side here, 12,000 feet, which is right across from 21. So I'm going to put that here. So what would that be? 12,000 is across, or the opposite. So if it's opposite over hypotenuse, okay, then I should know that I must use sine. Okay, so now we're going to go ahead and cross multiply. We're going to get x times sine 21 degrees is equal to 1,200. Now I need to do one more step to be able to leave the x by itself. I have to divide both sides by sine of 21. All right, that's going to eliminate and give us x is equal to 1,200 divided by the sine of 21. Okay, and all we got to do is we got to put that into the calculator to get our value. 1,200 divided by the sine of 21 degrees, and we're going to get 3,348.517, yeah, and so on. Okay, but the question asked us to round to the nearest foot. So we want the whole number. So we have the 8, but next to the 8 to the right is a 5. So we're going to have to round that up to 3,349 feet. Okay, that should be our response because we're rounding to the nearest foot. Okay, next up we're going to be talking about the Pythagorean identity. In the figure, we have a point xy. Let's say we're on a coordinate grid, so here that's why we have the x-axis, y-axis. Okay, and this point xy is on a circle, so that's what this is. It's on a circle with a radius of 1. So that's why there's a 1 here, because from the center to the edge of the circle, we have a 1. So then what we're going to do is we're going to consider this angle here to be called theta. Theta is a Greek letter. That's what we're going to use to name this given angle. So what we need to know is that x represents cosine of theta, and y, let's change the color here, y represents sine theta. Okay, and one other thing, because cosine equals adjacent over hypotenuse and sine equals opposite over hypotenuse, we should also know that tangent, let's change the color, match it. Let's say tangent of theta is equal to sine theta over cosine theta. Okay, so these are some of the identities that you're going to need to remember. And last but not least, because of the Pythagorean theorem, because cosine is x and sine is y, okay, we know that a squared plus b squared is equal to c squared. So then our identity that we're going to have here is cosine squared plus sine squared is going to be equal to 1. Okay, that's what we're going to be using on the next screen. Okay, so if we move here, we're going to go ahead and find trigonometric values when we're given one trigonometric value. So here we have cosine theta. Okay, and that's 3 over 5. Our goal is to find what sine theta is and what tangent theta is. Okay, so what we're going to use is we're going to use that Pythagorean theorem. So cosine squared theta plus sine squared theta is equal to 1. All right, so we know that cosine is 3/5, so we're going to go ahead and replace that with cosine. So I'm going to do 3 over 5, and then I'm going to do squared, because here we have a squared, here we don't. Okay, so that's going to get squared. I'm going to write the rest in a different color, plus sine squared theta is equal to 1. All right, so then here, what we're going to do is we're going to square 3 over 5. So then that's going to give us 9 over 25. 3 squared is 9, 5 squared is 25, so we have 9 over 25. Okay, next up, we're going to bring everything down. Sine squared theta is equal to 1. All right, so now I want to find, this is going to help me find sine. So what I'm going to do is I'm going to subtract 9 over 25 from both sides, minus 9 over 25, right? And then I'm going to write down what's the remainder here. So we have sine squared theta is going to be equal to, now 1 minus 9 over 25. I want to leave that as a fraction as long as I can. So I'm going to do the math up here, watch. 1 is equal to the same, well, 1 minus 9 over 25. That's what I'm trying to do. But 1 I can rewrite as 25 over 25 because that's equal to 1. And if I subtract 9 from 25, that's going to give me 16 over 25. All right, and because we have a squared, okay, we have this, we have to get rid of that, and we do that by taking the square root to both sides. That's going to end up giving us sine theta, so now the 2 is gone. This is going to give us our first value that we need, and we're just going to take the square root of each term in our fraction. So we have 16, square root of 16 is 4, over the square root of 25, which is 5. So our sine theta is 4 over 5. So I'm going to go ahead and put that over here just as a fraction. We're going to leave it there, 4 over 5. All right, if you didn't get that, go ahead and rewind the video so that you can see how we found sine theta. Now, on the previous screen, I mentioned this. Tangent theta is equal to sine over cosine. So I'm going to set that up right here. So tangent theta is equal to sine theta over cosine theta. All right, so what we're going to do is we're just going to substitute to find the tangent theta. All right, so sine, we found right here, it's in this box right here, 4/5. So I'm going to leave everything as a fraction until the very end. So 4 over 5 over, and then cosine was what we were first given, so 3 over 5. Okay, so what happens here is because these both have a 5 in the denominator, those basically get eliminated. So then tangent theta is just equal to 4 over 3. Okay, so let me show you how this works over here. So if I have 4 over 5 divided by 3 over 5, okay, so what you're doing is because it's division and you're dividing fractions, we will make it easier by changing it to multiplication. So the first fraction stays the same, 4 over 5, and then we're going to change it to multiplication, and this is going to change position. So we have 5 over 3. That's going to give us 20 over 15, which simplifies to 4 over 3. So that is our tangent theta. All right, so I hope you learned a lot in this lesson. This was the lesson in Chapter 9 that has been the most content-filled. So you should have learned the difference between cosine and sine. You should have known and understood how the complementary angles work with sine and cosine. You should be able to find the missing values of right triangles, so like the sides of a right triangle using sine and cosine. And then lastly, you should be able to use the Pythagorean identity to find trigonometric ratios. If you have any questions, comments, or concerns, please leave them in the comment section down below or leave me a comment in Google Classroom.